Hi guys, it's me. It is Sunday night and the Chiefs just won, so yay. Woo. And we're going to finish up some notes today on section 1.5, and then there'll be another assignment. And maybe I'm going to be able to put this all into one video because I learned how to use iMovie. We'll see. Okay, here we go. So I think this is a little bit funny. Section 1.5, continuity, continued, haha. So we have some properties of continuous functions. If the functions f and g are continuous at c, you can kind of see all the operations on those functions are also continuous at c, f plus g, f minus g, f times g, f divided by g. So that's good. Next, so again, pause when you need to. Take some time to write stuff down. Next, we have a theorem. Actually, one theorem with two parts. A polynomial is continuous everywhere. And that sort of makes sense when you think about what a polynomial is and what polynomial functions look like if we graph them. For instance, lines are considered polynomial. Quadratics are polynomial. Okay. Cubics, right, are also polynomial, and then we can get into even higher degree powers that are all polynomial, and so you can tell that those are clearly continuous everywhere. Then part B of this theorem says that rational functions are continuous at every point where the denominator is non-zero and has discontinuities at the points where the denominator is zero. And this is actually what we call asymptotic discontinuity, because when the denominator is zero, we have an asymptote on that graph, and obviously we would have discontinuity there. Even if you could think about even just the very basic 1 over x, which looks like this. Okay, we clearly have a discontinuous function at x equals 0 because there's an asymptote there. Okay, next, let's talk about some other kinds of discontinuity other than asymptotic. We have something called removable discontinuity. This one's actually going to be quite important. So the technical definition says if the limit of a function is equal to some number, okay, it exists and it is finite, meaning it's not infinity or negative infinity. But f of a is not defined, or this should say f of a. Maybe I need to make that list a little bit nicer. Let's go like this. F of a is not equal to L, we have what's called removable discontinuity. It's called removable discontinuity because we can actually remove the discontinuity. And here's how that happens. If f of a is not defined, the graph has a hole in it, but the hole can be filled by redefining the domain. By doing that, we remove the discontinuity, making the function continuous. So if we were to look at this particular function, f of x equals x squared minus 1 over x minus 1, we would find out that our domain is going to tell us that x cannot equal 1. Okay, and so what we might say is that f of 1 is not defined. Okay, so we have what is called removable discontinuity. Now, we can fill the hole at x equals 1. And here's how we do that. We find the limit as x approaches 1 of this function. And what we would find if we were to plug 1 into this rational function is that we would get 1 minus 1, which is 0, over 1 minus 1, which is also 0. 0 over 0 is indeterminate form. And if we have a limit that's indeterminate form, it means do something else. right now that do something else is generally try to factor. But I can factor x squared minus 1 into x plus 1 over x minus 1. Oh, times x minus 1, sorry, over x minus 1. The x minus 1's cancel, and I'm left with the limit as x approaches 1 of x plus 1, which is 1 plus 1, or 2. Okay. And so we were able to fill the hole. We fill the hole by defining f of 1 to equal 2. Okay, so that the limit as we approach 1 from the left and the right, because this is just a limit in general, is 2. There's a hole there, but then we fill it in, and we have our function. So we might say something like f of x is equal to x squared minus 1 over x minus 1. X is not equal to 1, and it's equal to 2 when x equals 1. Okay, and now we have written our function f of x. This is now a continuous function. Oh, sorry, need to move the screen down. There we go. This is now a continuous function because even though this is not applicable when x is not equal to 1 because it's undefined, we have now defined what's happening exactly at x equals 1. So we filled that hole and it's now continuous. Okay. So in general, what we're going to find is that removable discontinuities will occur when a factor in the numerator can be canceled with a factor in the denominator. Okay. And so that's exactly what happened here. Generally, that's because we can find the limit of the function. Okay, it is going to be a value, it's going to exist, and it will be finite. So we can find that limit, and then we can redefine our function to fill the hole. Okay. All right, next, let's see what we have. Oh yeah, these were the other kinds of discontinuity. That was removable discontinuity. We have also something called jump discontinuity. If the left-hand limit does not agree with the right-hand limit, we have jump discontinuity. We've seen this. I'm going to draw just a very quick, small graph, right? If I have some function that looks like this, right, this would be called jump discontinuity. Let's see if I can zoom in on that graph. There we go. Okay, there's literally a jump in the graph, okay, called jump discontinuity. And then lastly, we have if the left-hand limit and the right-hand limits approach positive or negative infinity, we have what's called infinite discontinuity, or that's also called asymptotic discontinuity. You'll see it called different things in different textbooks, and different people say different things. So it's either called infinite discontinuity or asymptotic. And again, think back when we talked about with that rational functions, we might have that. Okay. Next, we have the continuity of compositions. So again, we have a couple of theorems. We have a lot of theorems today, and then near the end, you'll see a couple of examples of the types of problems that you're going to need to be able to do on your homework. If the limit as x approaches some value of a function exists and is a finite number, that's what it means when you see the limit as x approaches some number of some function is equal to L. And this is g of x, and if the function f is continuous at L, then we can say that the limit of f of g of x is the same as f of the limit of g of x, or f of L, right? Because this limit was equal to L. We said that here. So then that's f of L. Okay. We have another theorem. Hopefully you guys can read that okay. This has two parts. If the function g is continuous at c and the function f is continuous at g of c, then the composition f of g is continuous at c. That's sort of restating this, although this is a little bit more algebraic in nature. And then part B of this one says, if the function g is continuous everywhere and the function f is continuous everywhere, then the composition f of g is also continuous everywhere. And next time, we're going to be looking at section 1.6, which is the continuity of trigonometric functions. This is going to be really important when we talk about those trigonometric functions and their continuity. So we'll hang on to that theorem for that purpose. Let's see. Sorry, trying to get back to my notes here. Yes. Next, I think we can get one more thing, or yeah, one more thing here. Absolute value. Here we go. What we're going to find out is that the absolute value of x is continuous everywhere. Therefore, the absolute value of a continuous function is also continuous. So think about this is sort of like doing a composition, right? If f of x is equal to the absolute value of x, and g of x is equal to, let's say, 4 minus x squared. This is a polynomial. We already discussed that polynomial functions are continuous everywhere. Then f of g, or f of g of x, or f of 4 minus x squared, or again, remember this composition means that we're going to go to this function. Everywhere there's an x, we're going to replace it with this. Let's put it down here a little bit. This would be then the absolute value of 4 minus x squared. Okay, so this is really another take on those compositions, right? If this is continuous and this is continuous everywhere, then their composition is continuous everywhere. So if the absolute value of x is continuous everywhere, the absolute value of a continuous function itself is continuous. Okay, f of g is continuous everywhere. Okay, next we have something called the intermediate value theorem, also abbreviated IVT. That's a pretty common abbreviation in calculus, so just FYI, that would be okay to write in your notes. So we're going to consider this graph. I have an x and a y axis drawn here, and I have an interval from a to b, and I'm going to draw some function. Okay, here's what it looks like. And I'm going to recognize that at the point where the x value is equal to a, I have a point. When the x value is equal to b, or on the x-axis, we have b, right? And I'm going to recognize also that this same point on the y-axis would be called f of a. Okay, this point here would be called f of b. And we're going to make some observations about this graph. First, the function is continuous. So let's start there. The function, f of x, is continuous on the interval from a to b. I think that's pretty obvious by looking at our graph. It's continuous in there. Okay, we'll say there is a value, this is kind of obvious, between a and b. Where the function is continuous. And maybe we're going to call that value, we're going to give it another little dot up here. And we're going to call that, over here on the y-axis, we're going to call that k. Okay, so it's k is just some value of y on the graph between a and b. Okay, so then we'll say, in fact, if f is continuous on the interval a to b, then f must take on every value of k between f of a and f of b. And so hopefully that sort of makes sense when you're thinking about this picture, right? We have in here between f of a and f of b, right, we have k values, okay? And it could be here, but it could be here, 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 right? All along this, we have something that's we're going to just consider to be k. And so what this is saying is that if we're continuous from a to b, that this k value will take on every single value between f of a and f of b, which kind of makes sense, right? It's going to take on different y values all along this curve, and all of them will fall between f of a and f of b. So let's say this was 3, and let's say this was 7, okay? Then we know that k is going to take on every value between 3 and 7. It's going to take on 3. It's going to take on 3.000001. That's right here next to f of a. It's going to take on 3.5. It's going to take on 4. It's going to take on 4.5. It's going to take on all these values all the way to 6.999999, okay? And all the way to actually 7 itself. So it's going. That's what we're saying over here. Okay? That might be all I need to say there. Yeah. So that's it. That's the intermediate value theorem. Okay? Now, we can use the intermediate value theorem, or the IVT, to approximate zeros. Remember that zeros are x-intercepts, they're roots, they're also called solutions of a function. So we have this, if f is continuous on a to b, and if f of a and f of b are non-zero, and we have opposite signs, meaning one is positive, one is negative, then there is at least one solution of the equation f of x equals 0 in the interval a to b. Yes, so let's think about a picture, right? Let's say that I have this graph. Okay, so we know that we have some point here. This is f of a. We have some other point here. Up here we have f of b. Oh, you can't see that, sorry. There we go. So really what this theorem is saying is that if it's continuous from a to b, we can see on this graph that it is in fact continuous. Okay. And f of a and f of b are non-zero. They're non-zero, right? One of them is a negative number, one's positive. And they have opposite signs. There is at least one solution of the equation. Remember, the solution is a 0 or an intercept. So we have at least one solution. Could we have more? Yeah, we could. If this graph had done some wiggling around in here, we could have had more than that. But we know we will have at least one solution of the equation from the interval from a to b. Okay, so that's basically what that theorem is saying, and that is what is going to help us be able to find a 0 of a function. And in fact, let's take a look at this example. Whoops. Oh, we're getting so close to being done. There's been a lot of writing today. Now this is going to be like a problem you're going to have on your homework. Show that f of x equals x squared minus 3x over 2x squared plus 4x has at least one solution in the interval 1, 4. Okay? All right, so the first thing we need to do is to show that f of x is continuous on the closed interval 1 to 4. And we can do that by looking at the domain. Okay, and if we look at the domain, we know that we have a rational function here, and the rational function, we know that we can't have 0 in the denominator. So we might say that this denominator, 2x squared plus 4x, cannot equal 0. We can factor that by taking out a 2x, leaving me with x plus 2. X plus 2, there. Then 2x can't equal 0. X plus 2 can't equal 0. So x can't equal 0, and also x can't equal negative 2. So we only have restrictions on our domain at 0 and at negative 2. Neither of these values lie within the interval that we're talking about. Therefore, this function is continuous on the interval from 1 to 4. Okay? So we might even say something about since the domain restrictions do not fall within the stated interval, f of x is continuous on 1 to 4. Okay? Okay. Now we want to show that f of a and f of b are non-zero and have opposite signs. Okay, so our interval is 1 to 4, so we're going to be looking at f of 1. F of 1 is going to be 1 squared minus 3 times 1 divided by 2 times 1 squared plus 4 times 1. Or on top we get 1 minus 3. On the bottom we get 2 plus 4, or negative 2 over 6, or negative 1/3. Okay. So f of 1, or f of a, is non-zero, not 0, and it's negative. Next, f of b, or in our case f of 4, we'll have on top then 2 squared minus 3 times 2 divided by 2 times 2 squared plus 4 times 2, or 4 minus 6. Uh-oh, what's going on here? Did I do that right? Maybe I wrote it down wrong. 3 times 2. No? Okay. 2 times is going to be 8 plus 8. This is also negative, though. I feel like I might have written something down wrong. So, but time's up on this video anyway, so I'm going to cut this off, check it out, and see what happened, and come back. We'll get it fixed. Okay, I'm sure you, well, now I don't even know if I had the screen tilted down where you could see it. But anyway, I had this all messed up, and if you could see it, I'm sure you saw that this was kind of a mess, and I put a 2 in place of x instead of 4. I found f of 2, which is negative. Interesting. And I found f of 4, which actually is positive. So here's what's happening. We actually found more than we wanted to. F of 1 is negative. F of 4 is positive. So we know that there has to be a 0 or a solution in between 1 and x equals 1 and x equals 4. Now, because I screwed this up and I actually found f of 2 here, and we found out that f of 2 is negative, we further narrowed down that now we actually have we know that there's a 0 or a solution to this equation between x equals 2 and x equals 4. That it crosses over that x-axis between 2 and 4. You wouldn't normally do this work because that was a little bit crazy on my part. So we might sum this up by saying, so since f of 1 is negative and f of 4 is positive, we might say something like by IVT, okay? And actually here's an interesting backwards E. There exists a solution between x, or no, we should say, maybe we should, sorry. There's a solution on the interval 1 to 4. Okay. All right. So that's what we're going to say there. Sorry, there's a little bit of activity going on in my home, and I'm a little distracted, but hopefully that all makes sense. Okay, we just have one more example to look at, and so we're gonna be looking at this one. And what I'm going to tell you, I'm going to have to stand this up a little. This is the last example. You're going to do some of these on your homework today. This type of problem is always a question on the final. Something like this is always on the final exam. So we're going to take a look at a function. We're going to find a value of k so that this function is continuous everywhere. Meaning that we need to make these two pieces of the graph meet when x is equal to 1. That's what's going to make it continuous everywhere. So basically the way we do that is we're going to say that the limit as x approaches 1 from the left, okay, which is going to be this piece of f of x, has to be the same as the limit as x approaches 1 from the right of f of x. Because again, if I'm just thinking about these graphs, what do I have here? I have some sort of line, and it's doing something like this, and then I have a parabola that might be doing something like this. And I want to find out what does the coefficient on this parabola have to be in order for these two to meet, the limit from the left and the limit from the right to meet. Okay, so that's really what we're looking at here. So, my pad of paper is going to fall. So I'm saying then that the limit as x approaches 1 from the left, that's going to use this piece, 7x minus 2, must equal the limit as x approaches 1 from the right. And now we're going to use that kx squared, okay, because that's where we're approaching from the right, greater than 1. And we're going to evaluate these limits. Well, the way I evaluate this limit is to just plug a 1 in. So 7 times 1 minus 2 must equal k times 1 squared, or 7 minus 2, or 5, is equal to k times 1, which is just k. So we just found out that k must equal 5. Now, some of you I know, because I know you, you've done it before. Look at me. I know you've done it. Don't do it. Some of you are thinking, oh, well, why do I have to go through all of this mess, right? This is not important. I can just plug the number in and I'm just making them equal to each other, and this will be a lot faster that way. But don't do that. Because remember how I'm trying to prepare you guys for this final exam, which I know is a long time away, but it's still important for us to get in the habit of doing things appropriately for it. That on the final exam, for a problem like this that is worth, probably 4 or 5 points, this is only worth 1 point. But this is worth 4 points. Okay? So knowing what it is that you need to show in order to find k is actually worth more points than finding k itself. So make sure that as you're working through the problems that you're writing what's appropriate in the way that you're going to find that information. Okay? Okay, that's the end of the notes for this section. So Here is your assignment. We're in section 1.5. You're going to be on page 49. And you're going to do 29 through 33 all. Then you're also going to do 35. And you're going to do 36. And you're going to do 47. Okay? That's your assignment for today. So work hard. And next time, again, we'll be talking about 1.6. You'll see the answers for this assignment. And then I'll talk to you a little bit about what's going to happen on Friday. Okay, see you guys.